Hello and welcome back. Today we'll be doing question 6 from the 2022 MAT paper. This question is for applicants in computer science, mathematics and computer science and philosophy only. This question is about influencer networks. An influencer network consists of n influencers denoted by circles and arrows between them. Throughout this question, each influencer holds one of two opinions, represented by either a triangle or a square in the circle. We say that an influencer A follows influencer B if there is an arrow from B to A. This indicates that B has the ability to influence A. The example in figure 1 above shows a network with A and B following each other, B and C following each other, and C also following A. In this example, initially, B and C have opinion square, while A has opinion triangle. An influencer will change their mind according to the strict majority rule. That is, they change their opinion if strictly more than half of the influencers they are following have an opinion different from theirs. Opinions in an influence network change in rounds. Each influencer will look at the influencers they are following and simultaneously change their opinion at the end of the round according to the strict majority rule. In the above network, after one round, A changes their opinion because the only influencer they are following, B, has a differing opinion, and the network becomes as shown in figure 2 above. An influencer network with an initial set of opinions is stable if no influencer changes their opinion, and a network with initial opinions is eventually stable if after a finite number of rounds it becomes stable. The network in the above example is eventually stable as it becomes stable after one round. Part 1. A network of 3 influencers without opinions is shown below. Is this influencer network eventually stable regardless of the initial opinions of the influencers A, B, and C? Justify your answer. Part 2. Another network of influencers without opinions is shown below. Is this influencer network eventually stable regardless of the initial opinions of the influencers? Justify your answer. Part 3. A partial network of influencers without opinions for B1 all the way to B8 is shown below. You may add at most 6 additional influencers, assign any opinion of your choice to the new influencers, and add any arrows to the network to describe follower relationships. Design a network that is eventually stable regardless of initial opinions and has the property that when it becomes stable, A has opinion square if and only if each of B1, B2, all the way to B8 had the opinion square at the start. Justify your answer. Part 4. You are given 2 influencer networks, N1 and N2, with disjoint sets of influencers shown below. Both are eventually stable. Suppose one of the influencers from network N2 follows the influencer X from the network N1. Is the resulting network guaranteed to be eventually stable? Justify your answer. Part 5a. Given a network with n influencers where the arrows are fixed but you are allowed to assign opinions to each influencer, how many possible assignments of opinions is possible? Given an influencer network and an initial assignment of opinions, explain how you would determine whether the influencer network is eventually stable. Justify your answer. Pause the video now to have a think, and once you're ready, restart to see if you were correct. Now, let's start with part 1. Here we have a network where A has opinion square, but B and C have the opinion triangle. If we advance this network by one round, we'll see that A will take on C's opinion, C will not change opinion, and B will take on A's opinion. Advancing this one more step gives us that A and B both believe in triangle, but C believes in square. And advancing this one more step returns us to the original situation. From here we can see that If there is one opinion that's different from the other two, then we have a non-stable system. This system will cycle between three different positions and will therefore never be stable. Now let's move on to part 2. Firstly, we'll number A and B with the number 0. Now we'll number all nodes influenced by A and B with the number 1. We'll then do this again, numbering all the nodes in the next level with the number 2, and so on until we have covered the entire structure. Here we'll notice that A and B are numbered 0, meaning that their opinions do not change. Similarly, we'll see that C, D, and E are numbered 1, meaning that their opinions could change on the first round, but not afterwards. F and G are numbered 2, meaning their opinions could change on or before the second round, but not afterwards. And H is numbered 3, meaning that their opinion could change on or before the third round, but again, not afterwards. Now we'll move on to part 3. Here we need to essentially construct an AND gate that takes in 8 inputs and 1 output. Given the definition of how influencers behave in the original question, we'll notice that one influencer being influenced by 2 other influencers acts exactly like an AND gate. Here we have 3 different setups where 2 influencers both influence one other. We'll notice that for the first one, the first influencer changes their opinion to square. However, for the second 2 situations, the influencer does not change their opinion and remains a triangle. Using this, we can explain the answer above. Here we have an AND gate, and we also have AND gates here, and here, and here. Similarly, on the next level, we also have AND gates here and here. Finally, for the last AND gate, we have an AND gate here, where D1 and D2 influence A. This system of nested AND gates ensures that when the system stabilizes, the opinion of A will be square if and only if all 8 influences B1, B2, all the way to B8 have opinion square at the beginning. Now we'll move on to part 4. Here we have the system as shown in the question. Now we'll consider what happens if A starts following X, if B starts following X, or if C starts following X. And I'll denote these with the colours red, green, and purple. Let's firstly consider the case where A starts following X before we start the simulation. A sees that X is a triangle, but that B is a square and therefore does not change. X is not influenced by anyone and therefore does not change. B is influenced by a triangle and a square and does not change. And C is influenced by a triangle and a square and does not change. Thus, the red condition, where A starts following X, is a stable system. Now we'll move on to the purple, where C starts following X before the simulation. Here we'll notice that A will change their opinion because B is a square, and C will change their opinion to a triangle because they follow a triangle, a square, and another triangle, X. B and X will not change their opinions. From here, we can advance another step. We'll notice that A, B, and X do not change their opinions, but C will change their opinion to a square. This is due to the fact that they follow now a square, and one triangle. Advancing this system again, we'll notice that this system is actually stable. Now we'll consider the green case, where B follows X. Advancing one step, we'll notice that X and C do not change their opinions. However, A will take on B's opinion because A sees that B is a square. B will see that A and X are triangles and B is a square, and therefore B will change their opinion to B triangle. From here, we can advance again and we'll see that X and C maintain their opinions, A is influenced by B's triangle opinion and changes their mind to a triangle, and finally B changes their opinion from triangle back to square because A and C are both squares. This system is not eventually stable as it oscillates between two states indefinitely. Now we'll move on to part 5. In part A, for each of the n influences, we have two possible opinions, square and triangle. This gives us 2 to the n possible initial opinions. Now we'll move on to part B. Firstly, we will run the simulation for 2 to the n steps and record the current state. We will then run the simulation for one more step and we will compare the final state to the state that we remembered. If these two states are identical, then we have already reached a stable state, so the original network is either stable or eventually stable. If the states are not identical, then the system will never be stable. This works because 2 to the n steps guarantees that all possible states generated by our initial starting position will all be reached. If one of these states is stable, then all subsequent states will be stable, and so the states at 2 to the n steps and one step further than that will be identical. If these two states are not identical, then none of our steps were stable, and so the system will never be stable. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.